Welcome, grade 12 class, 12 AP to period 4, day 26 of Coronachem on Monday, May the 11th, 2020. Today I'm going to review the mock test I gave you on Friday, and then tomorrow you'll have your real test. So the first question we had was 1714, in which you are asked to use information from Appendix D to calculate the pH of a solution that is 0.16 molar in sodium formate and 0.26 molar in formic acid. So in this case we can use the Henderson-Hasselbalch equation. First I found the Ka value of formic acid in the table at the back of the book. I took the log of it, negative log of it, to give the pKa, and that is the pH at which half of it is ionized if you put only one of them in solution. pH is equal to pK plus log of A minus over HA, where A minus is the formate anion and HA is the acid. A good way to remember this formula is to say AHA. The A is on top, A minus, the conjugate base is on top. So 3.74 plus log of 0.16 over 0.26 gives you 3.74 minus 0.21, and you get an answer of 3.53. Which brings us to the next question, 1744b. On 1744b, they ask, calculate the pH at the equivalence point in titrating a 0.1 molar solution of each of the following with 0.08 molar sodium hydroxide. And for B, it's lactic acid. So I'll show you what the equation looks like. Lactic acid is this. Sodium hydroxide. You're going to have to get in the way for the time being. The fact that this board is so tiny means automatically you're going to be blocking the whole view while I'm writing. I'll try to remember to stay out of the way for a few seconds each time so you can at least pause the video and see what I wrote. So I'm going to use the dilution equation because the dilution equation makes the assumption that the amount of moles of solute is the same before and after dilution. Well, in the same way, in a titration, the amount of solute is equal in both cases, the titrant and the thing that is being titrated. So the concentration of the lactic acid is 0.1 molar. The volume is, what is it? Just double checking. So I put 1. To make it easy to do the calculation, I guess I chose 1 liter as the volume. Why give yourself trouble? So 0.080 molar times volume 2, which is what you need. So V2 would have to be 1.25 liters. So the total volume at the end of titration, because you've done a titration, you're going to stop at the equivalence point. So that means the only thing that's left is the lactate anion. So what you're really finding is the Kb of lactate, and then finding out how many protons that pulls off of water to give you hydroxide. So you're going to have a slightly basic solution. So total volume at end of titration is 2.25. The 1 over here plus the 1.25 gives you 2.25 liters. So now you can calculate the concentration of lactate that results. Therefore, let's call La minus for lactate. The lactate ion concentration will be 0.08 molar, what it was initially, or 0.08 moles. Because it's 0.08 molar and you had 1 liter, you also have 0.08 moles. And 0.08 moles divided by the total volume of 2.25 liters gives you a concentration of lactate equal to 3.5 recurring times 10 to the negative 2 molar. Now we're going to use a kb of lactate to calculate the pH, the pOH that will result. I'm going to get rid of all this to give myself extra room. So Kb for lactic acid is Kw over Ka for the same. For sort of the Kb of the lactate anion is equal to Kw divided Ka of lactic acid. So 1.0 times 10 to the negative 14 over 1.4 times 10 to the negative 4 for lactic acid. So the Kb of lactate anion is equal to 7.1428 57 recurring times 10 to the negative 11. So we set up a quadratic formula because Kb is going to be equal to x squared over 3.5 recurring times 10 to the minus 2. I could do an ice table for you. Basically, it'll be the lactate anion plus water is going to reconstitute lactic acid and create hydroxide. You start off with, if you do an ice table, you'll recall that you had 3.5 times 10 to the negative 2 concentration. And X is going to dissociate. So equilibrium, it'll be 3.5 times 10 to the negative 2 minus X. This will be at 0. It'll be plus X at equilibrium. This will start off at 0 as well and go up by X and become X. So that's how you get this, which generates a trinomial in the end. X squared minus 2.53968 2539 times 10 to the negative 6. No, negative 12. Plus, I put it out of order in my notebook. 7.142857 recurring times 10 to the negative 11x, and all that equals 0. I plugged that all into my calculator. I mean, you could do it with the quadratic formula, but it's an ordeal. You waste a lot of time entering all the numbers because you want to make sure you get the right amount. Really, you could get away with using the approximation here. I just have this habit of wanting the exact answer, but you could very easily just ignore the minus x part and get the answer, and I guarantee you your answer would be very close to what I get by doing this. So x1 you get is 1.593602.432 times 10 to the negative 6, and that equals the hydroxide ion concentration. The other number is negative, something like 1.59 blah 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 times 10 to the negative 6. That's ignored. That's the correct number. So the total hydroxide, because the hydroxide concentration is so low from the lactate anion, it's within 1 order of magnitude to the concentration of hydroxide in pure water. So I'm not going to ignore that contribution because, as you recall, in pure water, you already had 10 to the negative 7 of hydroxide. So total OH minus concentration is going to be 10 to the negative 7 plus the 1.59, etc., times 10 to the negative 6. So what you get is 1.6. It hardly puts a dent in it. It hardly changes the answer, but you know, for people who like to be sticklers that way. So the pH is equal to negative log of that. I'll put the answer here because there's no room. You get 5.77. that's the sorry, that's pOH. pOH. So that means the pH is 14 minus 5.77, or sorry, because it's all squeezed in there. 8.23 is the pH that you get for that one. That's not overly tricky, just that last part where you add in the contribution of hydroxide from the auto-ionization of water. If you forget it, it goes from 1.59 to 1.69. It hardly makes it there. I think it might change the pH by 0.01. It's not something you would get marked wrong for. It's just a little aside. Okay, the next one is 1750. 1750 asks, a 1 liter solution saturated at 25 degrees with lead 2 iodide, plumbous iodide, contains 0.54 grams of plumbous iodide. Calculate the solubility product constant for this salt at 25 degrees Celsius. So we are going to first erase the board. So what's going to go on is plumbous iodide, which is a solid, does dissociate a tiny amount to produce plumbous ions and 2 iodide ions. And if you were to, well, they tell you that 0.54 grams of it dissolves. So 0.54 grams of it dissolves. You're going to find out the molar mass of plumbous iodide is 207.2. plus 2 times 126.90447 grams per mole. So what you get is 461. This is 461.00894 grams per mole. So that means you have 1.171343 879 times 10 to the negative 3 moles of plumbous iodide in solution. Now the KSP is going to be given by the concentration of plumbous ions times the concentration of iodide ions squared, which is going to be 1.17, etc., times 10 to the minus 3 times 2 times this number, because of course you get 2 equivalents of iodide, 1.17, etc., times 10 to the minus 3, all squared. What that gives you as an answer is KSP equals 6.428552997 times 10 to the negative 9, which you're only allowed to report as 2 sig figs, so you're going to say 6.4 times 10 to the negative 9 is the KSP of plumbous iodide under those conditions. The next question is 1773. Furoic acid has a Ka value of 6.76 times 10 to the negative 4 at 25 degrees Celsius. Okay. Here's a question for 1773.
Go figure, I didn't do it. Okay, so 1773 says fluoric acid has a Ka value of 6.76 times 10 to the negative 4, 25 degrees Celsius. Calculate the pH at 25 degrees Celsius. A solution formed by adding 35 grams of fluoric acid and 30 grams of sodium fluoroate to enough water to form 0.25 liters of solution. Oh, I see. You got to calculate, and then calculate the pH of a solution formed by mixing 30 milliliters of 0.25 molar and 20 milliliters of 0.22 molar of the conjugate base, and diluting the total volume to 125. This one is tricky because it asks you, it throws in some dilution. So let's do them all one at a time. It's going to take a while, but I think it's worthwhile. All right. So the first part, calculate the pH at 25 degrees of a solution formed by adding 35 grams of fluoric acid and 30 grams of sodium fluoroate. Let's look at what fluoric acid looks like on, as it goes HC5. So, sorry for all the wobbling. So 1773, fluoric acid looks like this. C5H3O3, and it dissociates into fluoroate, I guess, and a proton in aqueous solution. And you start off with 35 grams and 30 grams, and this is where you have to be careful because they say sodium fluoroate. So that sodium ion is going to change the amount of moles that are present. If you forget to put in the sodium part, you're going to get the wrong calculation of number of moles, and then everything's going to be off. And then the total of it is dissolved in 250 milliliters or 0.25 liters of solution. So we're going to use the Henderson-Hasselbalch equation, but before we can do that, we got to find out exactly how many moles of each of the two things are present. So let's find out the molar mass of both. The first one is fluoric acid. So that's made up of 5 times carbon, which is 5, so it'll be molar mass equals 5 times 12.011 plus 4 times 1.00794 plus 3 times 15.394 for the oxygen. And that equals 112.08496, and all this is dissolved in 0.25 liters, so that equals, you got 35 grams in the thing that weighs 112.08496 grams per mole, so that gives you the number of moles, and then all of that divided by 0.25 of a liter is going to give you the molarity for the fluoric acid. So divide this by 35, flip the bad boy over, you get 3.122. I don't know if I can fit all this in here. I'll do my best. You get 1.2490525 molar of the fluoric acid. Okay, and let's write that up here because I'm gonna have to erase later, and then I'm gonna lose that number. So 0.124900525 molar. Okay, let's do the calculation for the sodium fluoroate concentration. That's going to be sodium. So it's 22.98977 plus 5 times 12.011 plus 3 times 1.00794 plus 3 times 15.394 grams per mole.
So you get 22.98977 plus 5 times 12.011 plus 3 times 1.00794 plus 3 times 15.394. And what you get is
134.06679 grams per mole. And you have 30 grams of the stuff divided by 134.06679, which gives you, well, let's just do it all at once. Divided 30, flip it over, that gives you the number of moles. And then number of moles divided by the number of liters gives you a molarity of 0.895076253. All right, so let's write that up here. 0.895076253 molar. Now we're going to use the Henderson-Hasselbalch equation to solve for the pH. Let's erase all this and make room. We don't need that either for the time being. So pH is equal to pKa plus the log of A minus over HA. Do we know the pKa of furoic acid? 1773. Ka is 6.76 times 10 to the minus 4. So that means the pKa is the negative log of that. So log of 6.76 exponent negative 4 gives you 3.17. 0.533. I just throw them all in there. The numbers, that is. So 3.1700533 plus the log of A minus, the furoate concentration, 0.895076253 over 1.2490525. And that will give you the pH under these conditions. So let's do that. 0.895076253 divided 1.2490525 gives you 0.716. So you have 3.1700533 plus, take the log of that, you get negative 0.144720658. So the plus 3.1700533 gives you a pH of, oh, this point, I didn't see the times 10 to the minus 1. That's why I was looking at it. I was staring at it, goes, well, it doesn't seem looking, doesn't seem right. Something about it was bothering me, but that's why, because I didn't see the 10 to the minus 1 part. 533264. Okay. And you get a pH of 3.03. Let me just redo this calculation for quickly. I'll just do part of it. 0.895 divided 1.249. That gives you that. And the log of that gives you that. Yeah, it's 0.1. Okay. And then you add 3.17 and you get 3.03. That's good. So that's part A for that problem.
part B, it says a solution formed by mixing 30 milliliters of 0.25 molar and 20 milliliters of 0.22 molar. So in each case, what you have to find is the, you could do it two ways. You could find the concentration of each and then put the concentrations in, or just find the number of moles of each, but because they're mixing into each other, it's going to be this, they're all within the same volume, so it works out to the same ratio. So either way you can do it, and you'll get the right answer. So let's do that. Show you how that works. Part B. 30 milliliters of 0.25 molar furoic acid and 20 milliliters of 0.22 molar sodium furate, NaC5H3O3. So what you do is you say N is equal to NV. Just find the number of moles. Both numbers of moles are going to be put into the same solution. So whether you come out as a concentration or as a number of moles, the ratio of acid to conjugate base is going to be the same. So I'm going to do the easiest thing. I'm going to multiply number of the molarity M times the volume in liters, and we'll get a number for each one. So for the first one, let's call this the HA. So I'm going to have to rewrite that whole thing over. And we'll call that the conjugate base A minus. So you got 0.03 times 0.25. Remember, this is 31 thousandths of a liter, that's 0.03. So in the first case, using N equals NV, the N of HA equals 3/400, which is 7.5 times 10 to the negative 3 moles in a total of 50 milliliters. And the number of moles of A minus is going to be this times that, 0.02 times 0.22. And you're going to get 4.4 times 10 to the negative 3 moles also in 50 milliliters. So to calculate the concentration again is pointless because you're going to get just the ratio that has the same amount. So pH equals pKa plus log of A minus concentration over HA concentration. So you're going to get 3. You believe it? I forgot the pKa. I gotta redo it now. That Ka is. This is one of the disadvantages of having a minuscule board to write on. Right. 6.676 exponent negative 4 log of that equals, of course it's an error, log of 6.76 exponent negative 4. All right, 3.17. So it equals 3.17 plus the log of 4.4 times 10 to the negative 3 over 7.5 times 10 to the negative 3, which equals so it's 3.17 minus 0.231608587. Final pH you get from that is 2.93839. You're going to round that off to 2.94. That's your final answer. Okay guys, there's your mock test done. I'm gonna do something similar to that tomorrow. So study a little bit, and we'll see you tomorrow.